In this video, we're going to go through the discrete time Fourier transform properties and walk through those. There are some that we need to highlight. All of them are important, but some of them we need to highlight. Some are more important than others, if you want to say it that way. So as we go through, they're very similar to the continuous time, since my assumption is that all of you have looked at the continuous time Fourier transform. This is going to be very similar. The linearity still holds, the time shift still holds, frequency shift does, conjunction does as well, and then the time reversal does. But and then down, the convolution is the important one, as we had talked about, is that the convolution in time domain allows us to represent this thing as a multiplication in a Fourier transform or frequency domains, which basically what it does, and I'll get a little room here to talk about it, is just much like what we said before. If I had x of n coming in, and that went to a system, an LTI system, with the h of n, and then y of n was the output of this system. If you take a Fourier transform of each one of these items, we will have, of course, x of e to the j omega, and then we'll have h of e to the j omega. The names are about the same, so this will be called the function transfer function. This will be called the input. Fourier transform of input. Fourier transform of output would be y, capital letter Y, e to the j omega. And the power of this property is that since y used to be a convolution of h of n and x of n, now y of e to the j omega, the Fourier transform of the output, is going to be simply input, Fourier transform of input times, just simply times h of e to the j omega. And that's pretty powerful, because what it means that I can find the output by simply multiplying the input and the transfer function. By the way, if you don't remember, this h of j omega is called a transfer function. And this is useful because now I can look at system and relate the input and output by just simply multiplication, so we can work on very, very complex system very easily. Okay, so the reverse is also true. We don't use the reverse as much in the work we are doing, but some of the other, for example, we have the symmetry here again. And the other interesting thing is that a derivative in frequency domain is just a multiplication of the variable times the x of n. So if you have a derivative in frequency domain and you want to figure out the function, it's really easy. Bring it back and find it. So one of the, of course, the important function of having this set of properties defined and understood and having it nicely available is that a lot of the time somebody gives me a function, I can use this to quickly figure out what the behavior of the Fourier transform is, or when I look at a Fourier transform, I know the behavior of the original signal is. So that's the power of having these Fourier transforms available to you. Now, we don't have, so these are the relationship for the Fourier transform. And then another table that is useful is one of the most common Fourier transforms have been put in this table. As you can notice, from here to here, we also have a Fourier series, because these first 1, 2, 3, 4, 5, 6, 7 functions are assumed to be, or not assumed, they are periodic. So these are the periodic group, and the periodic group of functions will have both a Fourier series and a Fourier transform. If you go further down and look at the non-periodic function, these guys, of course, they don't have a Fourier series because they're not periodic, but they definitely have a Fourier transform. So we still are able to take them from a time domain, discrete time domain, to the frequency domain. So that's great. So that brings us kind of to the, so a lot of the time we can, as we showed in the continuous time format, we get a problem. We can take the problem either directly from we could see that the solution, so somebody wants us to take a given discrete time function and find a Fourier transform or reverse, we could simply go to the table here and figure that out. And or sometime in a little more complicated functions, we can go over to the properties function if you can't find it in the common one, and just maybe shift it or modify it a little bit so it looks like one of the standard one we have the answer to. And if none of those work, then we go to step 3, which is we have to basically use the original equations to derive them. So let's take a minute and do a couple of examples on each one of those, so we kind of have a sense of how that works. So let's say somebody comes up to you and say you're asked to find the someone asks us to find the Fourier transform of some discrete signal, and we need to do that. So let's say x of n, getting all the brackets right. Okay, so if that's the case, then we simply say if you want to find this, and then there's going to be 3 cases. One could be simple enough, so we can look at the table and find out. For example, they say x of n is equal to step function n. So, or let's say 5 step function n. We go over to this table. That's the immediate thing you want to do. You want to go to the table, take a look, see if there is a un. Yes, you sure enough, there is a u of n, and that the Fourier transform of x of n, which would be a capital letter X e to the j omega, is equal to this whole function here, 1 over 1 minus e to the j omega, plus summation of pi delta omega minus 2 pi k, and we're done. So that's the simplest one. It's in the table, you just look across, find it, and you're done. Another case might be a little more complicated, where it says you got to look at 2 things. So let's say x of n is equal to 5u, instead of just being n, maybe n minus 2. So now the question is shifted a little bit. So the question is, can I find the Fourier series for this one? If you simply go to this table and look around, you're not going to find it because you only have u of n. You don't have u of n minus something. So the question is, can I go over here and make it work? So you go over here looking for something that does the shift, and hopefully you will see that this allows you to the shift, and all you have to do is take whatever function is the regular x of n, which becomes x of e to the j omega, and multiply it by that e to the minus j n0. And in this case, n0 is equal to 2. So it'll basically, all I have to do is add this term, which is e to the minus j omega 2, and then after that I just simply take this and bring it down here. So that's case 2. That was case 1, case 2, and case 3 might be something that you just simply don't have in your list of function, and there is literally no way for you to convert it from here to there to figure it out. So a function might be x of n is equal to, so let's think of something that we don't necessarily have in there, and might be the system where I have e to the minus 5t plus j times t. Let's say that's the case, and I just don't have anything that looks like that in my list of things to use. Then I have to go back here and say, okay, if you want the Fourier transform, then I have to do this. So I'm sorry, that can't be an n, so a t, so it has to be an n because it's a discrete function. Then you say, okay, in that case, if you want an x of j omega, I have to go back to the original equation, which is a summation of this equation, which is summation of n going from minus infinity to infinity, x of n e to the minus j omega n, and so do that, and also have to also remember to make sure this actually does converge, because it has to converge. If I'm going to do that, it might not converge. Okay, and by the way, both of these should be really n, because this is a discrete, can't have t in it. All right. So once again, the property table can be used just simply as predicting, if I have the time domain stuff, predicting the Fourier transform behavior. If I have the frequency domain or Fourier transform, predicting the time domain. And it also can be used when somebody asks you to find a Fourier transform or inverse. If it's just in the table, might as well use it. If it's more complicated for case 2, maybe you can use some of the properties to convert the function so you can find it in the table to match the one that's in table. And case 3, which we really don't want to do unless we have to, we can't do the first 2 cases, which is to put it into the original. First of all, check to make sure it's converging, and then if it converges, put it in those 2 equations to move forward. As I'm looking at this, I realize that this probably will not converge unless I do something kind of like this. Then it would converge, okay? But anyway, so you put it in this function, solve it, and go through the whole process of figuring out what it is. That brings us to the end of the section talking about the properties of discrete Fourier transform.